Problem 11.77, we have a hay bale on a conveyor belt. As you increase this angle beta, there'll be a critical value of beta where it tips over, and a critical value of beta where it starts to slide. And so we want to determine what those are and see which one will happen first. So let's start with finding the angle at which it will tip. So let's draw this at some angle. Now, this will be the only point of contact where there's going to be the friction and normal forces acting once this starts to tip, because all of the weight will be loaded onto this corner. And so if we look at the torques involved, then the torque from the normal force and from friction are zero because they're at our origin point. And so since the torques have to all add up to zero, then the torque from the center of mass also has to be zero, which means that it's pointing straight down through the point A. So this is not drawn to scale properly, but so the torques from N and F equaling zero implies that the torque from the weight is also equal to zero, which means that the moment arm from the center of mass has to pass through this point. And so beta will also be here. And here we have 0.125 meters. So let's start writing this down. The arctangent of 0.125 meters. This is our opposite. Then the adjacent is going to be 0.25 meters, because this is half a meter tall and a quarter meter wide, so 1/8 and 1/4 meters. And so this is 27 degrees, where it tips. And now when it's ready to start sliding down, then the static friction has its maximum value, which is the static coefficient of friction times the normal force. So we need to figure out what that normal force is. And so we now use our equilibrium conditions involving the forces in the x and y directions. So in the y direction, we're going to have that the normal force minus mg cosine beta is equal to 0. So F sub s equals mu s mg cosine of beta this is using, I'm sorry, this is using coordinates that are inclined with the hay bale. So that's why there's only, that's why the normal force is only in the y direction and the friction force is only in the x direction. Then we also have that F sub s minus mg sine of beta equals 0. Right. And so then we need, well, so we have two expressions for the normal force, and so a thing minus itself has to equal 0. So mu sub s mg cosine beta minus mg sine of beta that looked like a beta equals 0. And so then we can see that tangent of beta is equal to the static coefficient of friction. And so if beta has a value of 0.6, the angle is 31 degrees for it to slip. Now for part B, the angle at which it tips can't change because none of this involved the coefficient of friction. So this is still going to tip at 27 degrees. And then if we, you know, you don't have to redo the calculation. We know that our beta that should look like a beta is equal to the arctangent of the coefficient of friction, which is 0.4, and that is 22 degrees. And so if the coefficient of friction is reduced, then it will slip before it tips after some, you know, value of the coefficient of friction in between 0.4 and 0.6. And this makes sense because, you know, if it's at a given angle and it's not tipping, then if you reduce the coefficient of friction, you would expect it to start slipping as you reduce the coefficient of friction. So everything sort of adds up here.